Module 6, Lecture B, Simple Text Parsing. By the end of this lecture, you will be able to use split to break strings into lists based on separators, process each part of a split string using loops and simple conditions, and apply basic parsing to simple text formats like comma-separated values. Splitting text basics. Using split. In many programs, you need to break a long piece of text into smaller, meaningful parts, and this is done using a split operation. Splitting takes a continuous string, such as a sentence or user input, and divides it wherever a chosen separator appears, like a space or a comma. The result is a set of shorter strings that you can handle one by one. This process is a basic step in simple text parsing and makes it easier to analyze or process each part of the text independently. When information like a full name, a date, or an address is stored as one long piece of text, it is hard to work with each part separately. By splitting the text at spaces or other separators, you break it into smaller parts, such as first and last names or day, month, and year. This makes each component easy to access and manage. Overall, splitting text into pieces is a powerful way to organize and analyze data more effectively. Splitting text is an important step in many real-world tasks, such as pulling separate values from one form field or isolating timestamps in log files. It can also be used to break sentences into individual words for counting or searching. By dividing raw text into smaller pieces, you turn it into organized data that is easier to process and analyze further. Python code. Using split. This material explains that the script demonstrates how the split operation breaks a piece of text into smaller parts. It uses simple examples with names and dates to make the idea clear. For each example, it shows the original string and then prints the list of parts created after splitting. The focus is on understanding how text is divided into separate elements. This line explains that the script only relies on Python's built-in features, so no extra libraries or packages are required. As a result, you do not need to run any installation commands before using it. This makes the setup easier and helps the script run consistently on different systems. We begin with a string that holds a full name including first, middle, and last parts. We then apply the split method, using a space as the separator to break this full name into a list of separate name components. Finally, we display both the original full name and the resulting list so we can see how the split operation divided the string into individual parts. We begin with a date written as a single string using dashes to separate the month, day, and year. We then apply the split method, telling it to use the dash as the separator. This divides the date into three parts: month, day, and year, stored in a list. Finally, we display both the original date string and the resulting list so we can compare the initial format with the split version. We begin with a string that holds a short address containing the city, state, and zip code. We then apply the split method using a space as the separator, which divides the address into its individual parts. This produces a list with the city, state, and zip code as separate elements. Finally, we display both the original address and the resulting list to show how the split method breaks the text into components. This script shows how to use the split method to break a string into a list of parts based on a chosen separator. It demonstrates this with a full name split into first, middle, and last names using spaces, a date split into day, month, and year using dashes, and an address split into city, state, and zip code using spaces. In each case, it prints the original string and the resulting list to illustrate how split can turn structured text into smaller, easier to work with pieces. Choosing split separators. When we divide text into parts, the most important choice is the separator, or boundary, that marks where one piece ends and the next begins. This separator might be a common character, such as a comma, space, or semicolon, or a special symbol like a vertical bar or dash. The separator you choose determines whether you get clear, meaningful segments or a confusing mix of fragments. Overall, the goal is to match the separator to the structure of the text, so each logical unit, such as a word, field, or sentence, is cleanly separated. When choosing a separator in text, pick a character that clearly divides the parts you care about and does not appear inside those parts. For example, commas often work for separating city names, but hyphens can be problematic for full names if some surnames are hyphenated. If a line contains both commas and semicolons, you need to understand their roles, since semicolons may separate major fields while commas separate smaller details. In such cases, using semicolons as the main separator usually produces more meaningful segments, while relying on commas alone can break the text into smaller, less useful pieces. When text uses the same character in different ways, such as commas, both to separate attributes and inside quoted phrases, treating every comma as a separator can break important information apart. In these cases, it is better to choose a different boundary marker, like a new line for each record, and then handle the structure within each record separately. The main idea is to carefully analyze the text, look for consistent patterns, and select separators that match how the data is actually organized. This leads to cleaner, more coherent parsing results. Python code. Choosing split separators. We will explore how to choose useful separator characters when splitting a string into parts. By applying different separators to the same text and comparing the results, you can see how each choice affects the pieces you get. This comparison shows that some separators lead to cleaner, more meaningful segments, while others create fragments that are less useful. The goal is to understand which separators best match the structure of the text you are working with. This line is a placeholder comment reminding you where to add a command to install any needed libraries. It signals that the code may depend on external packages and that they must be installed for the script to run correctly. This is especially important when sharing code with others who might not have the same environment or libraries already set up. We create a string called shopping list that holds several grocery items separated by commas. This structure is useful because we can later split the string at each comma to isolate the individual items. Once split, each grocery item can be processed or handled separately. This approach makes it easier to work with multiple items stored in a single piece of text. We start with a single string that holds a shopping list, where each item is separated by a comma. By using the split method with a comma as the separator, we break this string into separate pieces. Each grocery item becomes its own element in a list. This structure makes it easier to handle and process each item individually in later steps. This code takes a shopping list stored as a single string and splits it into separate items using the comma as a divider. Each grocery item becomes its own element in a list. The result is a clean, organized collection of individual items that is easier to work with and display. We define a string called city trip that contains several city names, each written with a hyphen as part of the name, such as New York or Los Angeles. The cities in this string are separated by commas. This setup is used to show how choosing different separators, like commas or hyphens, affects how the string is split into individual items. It also highlights what happens when the separator you use for splitting might also appear inside the items themselves. We have a string that contains several city names separated by commas, and we use the split method with the comma as the separator. This breaks the original string into a list where each item is one complete city name. Because commas only appear between the names, using them as the separator keeps each city name intact. This prevents any accidental splitting inside the names themselves and cleanly separates the cities into individual elements. This line prints the result of splitting the city trip text using a comma as the separator. Using the comma keeps each full city name together instead of breaking it into smaller parts. The output is a list of complete city names, which shows that choosing an appropriate separator helps preserve meaningful data in the split results. In this example, a string of city names that already contain hyphens is split using a dash as the separator. Because the dash is part of the city names themselves, the split operation breaks each name into meaningless fragments. This shows that if you choose a separator that appears inside your data, you will not get complete, useful pieces. Instead, you should pick a separator that clearly separates items without cutting them apart. This example shows what happens when you split a string using a dash as the separator. Because some city names themselves contain hyphens, the split operation breaks those names into incomplete pieces. As a result, the output is messy and the city names are no longer meaningful. The key idea is that choosing an inappropriate separator can damage the structure and usefulness of your data. We define a log entry as a single string that uses vertical bars to separate its different parts, such as the date, time, event description, and sensor ID. This consistent structure makes it easy to later split the string into its individual fields by using the vertical bar as a separator. Organizing log data in this way helps us quickly access and work with specific pieces of information from each entry. In this example, a log line uses vertical bars to separate key fields, like the date, time, event description, and sensor ID. By calling the split method with the vertical bar as the separator, the log entry is broken into distinct parts, each corresponding to one of these fields. This approach keeps each piece of information intact and makes it easy to access and use for later processing or analysis. The code splits a log line using the vertical bar character as a separator, because that symbol marks the boundaries between key fields like date, time, event description, and sensor ID. Splitting the string at these points cleanly extracts each field. This makes the log data more meaningful and easier to process. The printed output shows these fields as separate items in a list, illustrating how choosing the right separator helps organize structured data. This script shows why choosing the right separator when splitting text is important for clear and accurate results. It first splits a shopping list and a list of city names using commas, which keeps each item or city name intact, even when city names contain hyphens. When the same city list is split using dashes, the city names are broken into meaningless fragments, demonstrating a poor separator choice. Finally, it splits a log entry using vertical bars to cleanly separate each field. Overall, it highlights that your separator must match the structure of the data to avoid confusion and preserve meaning. Trimming extra spaces. When you split text, extra spaces can cause inconsistent results, especially in lists of names separated by commas. Some names may include a space after the comma, while others do not, which can break comparisons and searches because the versions with and without the leading space do not match. To avoid this, it is important to trim spaces after splitting, so each piece of text is clean and consistent. This is especially vital when working with text that has been manually edited or copied. Trimming extra spaces means removing unwanted white space from the beginning and end of text after it has been split. This white space can be spaces, tabs, or line breaks that often appear in copied or pasted content. Without trimming, responses that look the same, like a color with a space before or after it, are treated as different values by your program. By trimming these extra characters, you make all responses consistent, which makes them easier to count, compare, and analyze accurately. Trimming extra spaces is important in real-world tasks, like managing product categories, blog tags, or email lists, because stray spaces can create duplicates, break lookups, and produce confusing results. By trimming each piece of text right after you split it, you make sure all later steps, such as filtering and reporting, work with clean and consistent data. This simple habit helps maintain data quality and keeps every item standardized for accurate processing and clear communication. Python code, trimming extra spaces. This script demonstrates how extra spaces can change the way text is split into pieces. It then removes those spaces using a trimming function to clean up each piece. Finally, it compares the split results before and after trimming to show the effect of removing extra spaces. This line is a placeholder comment reminding you that you may need to install an external library using a package manager. It is used when a script depends on packages that are not part of the standard Python library. Including this reminder helps anyone running the code make sure they install all required dependencies before executing the script. We begin with a text string that holds a list of names separated by commas. but the spaces around the names are inconsistent. Some names have extra spaces before or after them. This is done on purpose to show how inconsistent spacing can affect text processing. Later in the script, we will see how to clean up these spaces so the names can be handled correctly. This code takes a single raw string containing several names separated by commas and breaks it into a list of individual names. It does this by using a split operation with the comma as the separator. The result is a collection of separate name strings that are easier to work with, although some may still include extra spaces at the beginning or end. The code first prints a message to indicate that the next output will show the list of names before any spaces are removed. It then displays the names exactly as they appear after the split operation. This lets you clearly see any leading or trailing spaces and other spacing inconsistencies. These issues will be cleaned up in the following steps. We use a list comprehension to go through each name in the list of split names and apply the strip method to it. This method removes any spaces at the beginning or end of each name. The result is a new list of trimmed names where all extra spaces have been cleaned up. This makes the names more consistent and easier to process or compare later. We now display the list of names again to show how they look after removing extra spaces. This lets us see the cleaned, consistent format of each name. Having names in a uniform format makes them easier to process and use in later steps. It also helps prevent errors that can occur when data is messy or inconsistent. First, we print a message to show that we are about to display the lengths of the names before trimming any spaces. Then we use a list comprehension to find the length of each original name, which still includes any leading or trailing spaces. By printing these lengths, we can see how much extra space each name had before we cleaned them up. We now print the lengths of each name in the list after trimming, which shows how many white space characters were removed. Using a list comprehension, we go through each cleaned name and calculate its length. Comparing these lengths with the originals reveals the change in character count after spaces are stripped away. This gives a clear view of how the data has been cleaned. This script shows how extra spaces in text can interfere with processing and comparisons, and how to clean them up. It starts with a string of names separated by commas, which produces a list where some names have unwanted spaces at the beginning or end. It then removes these spaces using a trimming method to create a cleaner list. By comparing the lengths of the names before and after trimming, it highlights how hidden white space is removed. This cleaning step is important for keeping text data consistent and reliable for later analysis or comparison. Processing split parts, looping through words. After you split text into parts, such as words in a sentence, the next step is to loop through each part one by one. A loop lets you examine every piece and decide what to do with it, like counting, changing, or skipping it. This split and then loop process is essential for breaking a string into smaller, manageable pieces, so you can analyze or modify the text without dealing with the entire string at once. When you loop through parts of a split string, you can apply conditions to treat each piece differently based on what it contains. You might check whether a word matches a specific term, signals urgency, has a certain length, or consists only of letters. In survey data, this lets you count how often words like excellent or poor appear. And in email subjects, it helps you flag urgent messages. Overall, this approach helps you systematically extract meaning from raw text. When you loop through pieces of text, you can turn raw data into useful information, such as summaries or cleaned-up versions. As each word or field is processed, you decide whether to keep it, modify it, or use it to update counts. For example, in a web server log, you might pull out user IDs or count how many times each page is requested. And in a meeting transcript, you might track how often certain topics are mentioned. This looping approach lets you systematically choose what to keep, change, or discard, so the original text becomes more organized and informative. Python code, looping through words. This example shows how to loop through the words in a sentence after splitting it into separate parts. You first display the original sentence, then break it into individual words. Inside the loop, each word is processed one at a time. Finally, you present a summary that includes the original sentence, the list of split words, and the results of the processing. The commented line about installing a library is not actually required for this script to run. It serves mainly as a placeholder or reminder, showing where you might add a library installation command in the future. In other words, the code works without it, and the comment is just there for potential future needs. We begin by creating a variable that stores a short customer review describing a product as absolutely excellent and worth every dollar. This review serves as our sample text. We will later use it to demonstrate how to analyze the sentiment expressed in a sentence. The code takes a sentence stored in a variable and breaks it into individual words using a splitting method that separates the text at each space. The resulting collection of words is stored in another variable. This step is important because it allows the program to handle each word on its own. Once the words are separated, later parts of the code can, for example, check each word to see if it indicates positive sentiment. We begin by printing the original review sentence so we have a clear reference before any processing happens. Seeing the unmodified sentence first makes it easier to follow how each later step changes it. This initial output serves as a baseline for understanding all subsequent transformations and analyses in the code. We display the list of words that were created by splitting the original sentence. Seeing each word as a separate item in the list makes it clear how the sentence was divided. This view also makes it easier to work with the words later in the code, since each one can be processed individually. We begin by creating a counter called positive count and setting it to 0. This counter will track how many positive words appear as we go through the sentence. Each time we find a positive word, we increase the counter. Starting from 0 makes it easy to measure how many positive words are present and later judge the overall sentiment of the review. We start by defining a list of words that signal a positive tone, such as excellent, worth, absolutely, and totally. Later, we check whether any of these words appear in the sentence we want to analyze. By using this predefined list, we can quickly estimate the sentiment of a review. We do this by counting how many of these positive words are present in the text. We go through each word in the list and convert it to lowercase so that capitalization does not affect our comparison. This standardization step makes sure that words like happy and happy are treated the same. It is essential for reliably checking whether a word matches any item in our predefined list of positive words. A program checks each word in the review by converting it to lowercase and seeing if it appears in a list of positive words. When a match is found, it increases a counter that tracks how many positive words occur. By counting these positive words, the code helps determine the overall sentiment of the review. The program displays how many positive words it found in the sentence by printing the value stored in the positive count. This number summarizes how many words were recognized as positive. The result is based on comparing each word in the sentence to a predefined list of positive words. This code judges the overall sentiment of a review by counting how many positive words it contains. It uses a simple condition. If the number of positive words is greater than 1, it labels the review as having a positive sentiment. If this condition is not met, it treats the review as neutral. In this way, the presence and count of positive language directly determine the sentiment classification. This script performs a simple sentiment analysis on a customer review by splitting the sentence into individual words and comparing each word to a small list of positive terms such as excellent and worth. It first shows the original sentence and the resulting list of words, then counts how many of those words match the positive list. Based on this count, it reports how many positive words were found and uses that number to judge the overall sentiment. If more than one positive word appears, the review is labeled as positive. Otherwise, it is considered neutral. This demonstrates a basic approach to text processing and sentiment analysis using Python's string handling features. Cleaning split parts. After splitting text into parts, the next step is to clean each piece so it can be processed reliably. This means removing extra spaces, getting rid of stray punctuation, and standardizing capitalization. Doing this ensures that responses like yes, with different spacing or punctuation, are treated as the same value. These transformations turn messy text into a consistent form, which makes it easier to search, count, and categorize later. When working with many text entries, such as product tags, it is important to clean them before analysis so that small formatting differences do not cause problems. Tags like eco-friendly, and eco-friendly may look different because of spaces and capitalization, but they should be treated as the same category. By trimming extra spaces, converting everything to lowercase, and standardizing punctuation, you make these entries consistent. This cleaning step lets your loop apply conditions reliably and ensures consistent classification without errors from minor formatting differences. When cleaning split text in real applications, the goal is to remove or adjust characters that could interfere with the task while keeping important ones. For example, you might strip trailing commas or periods from names, but keep hyphens, or remove extra symbols and decorative characters from social media text. As you process each piece of text, apply the same checks, such as removing unwanted symbols and skipping empty parts. Using these consistent, predictable steps helps you build reliable routines that can handle messy or loosely structured text effectively. Python code, cleaning split parts. This lesson shows how to clean pieces of split text using simple string methods so they can be compared reliably. You will see how to trim extra spaces, remove punctuation, and convert words to lowercase. By applying these basic cleaning steps, beginners can make sure that different text parts are in a consistent form before comparing them. This line in the script is simply a placeholder to indicate where you would install any required libraries. It serves as a reminder to make sure all dependencies are installed before running the code. In this particular script, no external libraries are actually needed, but including such a placeholder is common practice. It is especially useful if the code might later be expanded to use additional library functions. We begin with a text variable that holds a survey response written in a messy way, with inconsistent capitalization, spacing, and punctuation. This setup is intentional and represents the kind of unclean data often found in real-world situations. By working with this imperfect text, we can focus on how to clean and standardize it. The goal is to show effective techniques for preparing raw text data so it is ready for analysis. We begin by printing the original text before applying any cleaning steps so we can see the data in its raw form. This gives us a clear reference to compare with the cleaned version later. Viewing the unprocessed text makes it easier to spot issues like inconsistent formatting, extra spaces, and unnecessary punctuation that need to be fixed. The code processes the raw text by splitting it at spaces, turning the string into a list of separate pieces. Each piece represents a word or punctuation-based element from the original text. This separation is important because it isolates individual components, making it easier to clean and further process the text in later steps. We begin by defining a set of punctuation marks, such as commas, exclamation points, question marks, and periods, that we want to remove from the edges of text segments. Using this list, we systematically clean each part of the text by stripping away any leading or trailing punctuation. This process helps normalize the text and prepares it for later processing steps. We begin by creating an empty list called cleaned parts, which will store the processed segments of text. This list starts out empty, so it can be filled only with text that has been properly cleaned. As we remove unwanted characters and normalize the formatting, each acceptable segment is added to this list. This approach ensures that the final collection of text is tidy, consistent, and meets our cleaning criteria. We go through each element in the list of parts so we can process every segment of the split text on its own. For each part, we clean it by removing unwanted characters and normalizing the text. This prepares the data for reliable comparisons later. By handling each piece separately, we make sure the entire original string is properly cleaned and transformed. First, we remove any extra spaces at the beginning and end of the current text part using a trimming method. This step cleans up the text so it does not contain unnecessary white space. As a result, each piece of text is neater and better prepared for any further processing we need to do. This code repeatedly checks the first character of a trimmed string and removes it if it is an unwanted punctuation mark. Each time such a character is found at the beginning, the string is shortened to exclude that character. The process continues until the first character is acceptable or the string becomes empty. As a result, all leading punctuation is completely stripped from the string. This part of the code cleans each text segment by removing unwanted punctuation from the end. It uses a loop that repeatedly checks the last character and, if it is in the list of unwanted punctuation, trims it off. The loop continues until the final character is no longer one of these marks. This ensures that each text part has no trailing punctuation before the next cleaning step is applied. The code changes the trimmed text to all lowercase so that every part has a consistent format. This normalization removes differences caused by capitalization. As a result, later comparisons between pieces of text become more accurate and reliable. This step is essential for dependable text analysis. The code checks whether each cleaned piece of text is empty or not. If a piece is not empty, it is added to a list of cleaned parts. This way, only meaningful text remains after removing unwanted characters and normalizing the content. As a result, the final list contains only useful, non-empty strings. Finally, the code prints the list of cleaned parts, showing the outcome of all the transformations applied to the original text. This output provides a clear view of the cleaned and normalized words. It is an important step for checking that the cleaning process worked correctly and that the data is ready for accurate comparisons or further analysis. This script shows how to clean and normalize messy survey text so it can be compared consistently. It starts with raw text that has irregular spaces and punctuation, then splits the text into separate parts. Each part is cleaned by trimming extra spaces, removing punctuation, such as commas, exclamation marks, and question marks, and converting everything to lowercase. Empty results are discarded, and the script outputs a final list of cleaned text elements ready for reliable analysis. Filtering split results. After splitting text into parts, the next step is to filter them so only the pieces that meet certain conditions are kept. You examine each part and check criteria such as length, capitalization, or whether it avoids common words. As you loop through the list, you keep only the parts that fit these rules and place them into a new collection. This selective filtering is essential for cleaning data and preparing it for further analysis. Filtering is important when working with text that contains irrelevant information. For example, in a web server log, you can split each line into parts, such as timestamps and status codes. Then keep only the lines where the status code indicates an error. In survey data, you can similarly remove empty or placeholder answers by checking each response against certain conditions. Overall, this process involves looping through the data, examining each component, and keeping only the parts that meet your criteria for further analysis. When working with text, you often apply several simple filters together to clean it up. For example, you might keep only pieces that are not empty, are not just punctuation, and are not on a list of unhelpful terms. As you loop through the text, you apply each rule and only keep items that pass them all. This layered filtering turns messy raw text into a more useful form for tasks like counting word frequencies or finding themes. And practicing these rules is essential for handling real-world text effectively. Python code, filtering split results. This lesson shows how to filter parts of a split sentence using simple loop conditions so that you keep only the useful words. You will compare the original list of words with the filtered list to clearly see which words were removed. If needed, you may also install any required library before running the example. We begin with a single sentence that contains a mix of common words and punctuation, and use it as our source text. This sentence serves as a realistic example for demonstrating how to filter language. The goal is to extract the meaningful words from it, while ignoring less useful ones. This setup allows us to focus on the core idea of identifying important terms within everyday written language. This code takes a sentence and splits it into individual words by using a space as the separator. Each word between spaces becomes an item in a new list called words. This approach is a standard technique in text processing and makes it easy to work with or analyze each word separately. We define a list of stop words, which are common short words that usually do not add useful information for analysis. Examples include words like the, and over. This list is used later to filter these unhelpful words out of our text data. By removing them, we keep only the more meaningful words for further processing. We begin by creating an empty list called filtered words, which will hold only the words that pass our filtering rules. Starting with an empty list gives us a clean starting point. As we go through each word in the sentence, we add it to this list only if it meets the conditions we have defined. This way, the final list contains just the useful processed words. We process the sentence by looping through the list of words created when the sentence is split. This lets us look at each word one at a time. For every word, we check certain conditions to decide whether it is useful. Only the words that meet these conditions are kept in the final filtered list. The code converts each word in the list to lowercase so that capitalization differences do not affect comparisons. By standardizing the case, it treats words like the and the as the same. This makes it easier to reliably check words against a list of stop words or apply other filtering rules. Overall, using lowercase ensures consistent and accurate word matching. The code takes a word that has already been converted to lowercase and removes any period characters at the end. It does this using a stripping operation that cleans off trailing punctuation. This step standardizes the word's format so it can be processed more reliably. As a result, tasks like filtering or comparing words are not affected by extra periods at the end. The code keeps a word only if, after cleaning, it has more than 3 characters and is not in the stop word list. This means it filters out very short words and common filler words. As a result, only more meaningful, content-rich words are passed on for further processing. The code adds each cleaned word that passes the filters to a list of filtered words. This step is important because it gradually builds the final set of words that are not stop words and are longer than 3 characters. By collecting only these qualifying words, the code creates a refined version of the original sentence that keeps just the meaningful content. The code displays the original list of words that were split from the sentence so you can see the starting point before any filtering is applied. This lets you compare the unfiltered words with the filtered list to see which words were removed and which were kept. In this way, it provides a simple visual check that helps you verify and understand the filtering process. At the end, the code prints the list of filtered words. This list includes only the words considered useful after applying the earlier filtering rules. In other words, it shows the remaining words once common short words, and any words with fewer than 4 characters have been removed. Displaying this list makes the final filtering results clear and easy to review. This script takes a sentence, splits it into individual words, and filters out less useful ones to clean the text. It removes very common short words, drops any word shorter than 4 characters, strips periods at the end of words, and converts everything to lowercase. The result is a shorter list of more meaningful words. It then prints this filtered list alongside the original words to show how basic text filtering can prepare data for further analysis or processing. Parsing simple formats. Working with CSV text. CSV files store data so that each line is a record and each value in that record is separated by a comma, much like rows and columns in a spreadsheet. Parsing CSV means splitting these lines into individual data fields, such as names or numbers, so they can be processed by a program. This skill is important because many real-world datasets, including logs and configuration files, are provided in CSV format and must be parsed correctly to be useful. Parsing a CSV line means turning a raw comma-separated string into structured data fields, such as first name, last name, and email. Once separated, these fields can be stored, listed, or checked. For example, to verify that an email contains an @ symbol or that a price is a valid number. In a library file of book details, parsing allows you to build a searchable database, filter books by publication year, and report on how many titles each author has. This process is essential for organizing information so it can be analyzed and used efficiently. CSV files are usually easy to work with, especially in simple cases where commas separate each field and the fields contain only plain text without extra commas or line breaks. In these situations, you can reliably treat each comma as a boundary and extract the values in between, which is enough for basic tasks like handling customer lists or simple sensor logs. As you gain experience, you will encounter more complex CSV files with features like quoted fields or missing values. But starting with these straightforward examples helps you build confidence in working with structured data. Python code, working with CSV text. This material shows how to parse simple CSV-style text lines in Python using only standard built-in features. It demonstrates splitting each line into separate, meaningful data fields and then printing the parsed records. The goal is to give beginners a clear, friendly understanding of how raw CSV text can be turned into structured data without needing to install any extra libraries. We begin with a short block of text formatted like a simple CSV file. It contains 3 book records, and each record includes information such as the title, author, year, and shelf location. The records are separated by new lines and the individual pieces of information within each record are separated by commas. This structure imitates a basic CSV file, so the data can be easily parsed and manipulated in later steps. The code takes a block of text that is formatted like a CSV file and splits it into separate lines, where each line represents one book record. It does this by using a split operation with the new line character as the separator. As a result, the original text is broken into individual pieces, making it easier to process each book's data independently. The code takes the first line from the list of lines produced by splitting the CSV text by new lines. This first line is treated as the header row, containing the names of the columns, such as title, author, year, and shelf. By storing this header line, the code defines the structure of the data. This allows all the remaining lines to be parsed and understood according to these column names. The code reads the first line of the CSV text, which holds the column headers, and splits it at each comma to create a list of column names. Each item in this list represents one field in the data. These headers are then used as keys in dictionaries that store each book's information. This allows the program to access each piece of data in a structured way based on its corresponding field name. We begin by creating an empty list called parsed books, which will hold the data we extract from the CSV text. Each time we process a line from the CSV, we turn it into a dictionary that represents one book record. We then append this dictionary to the list. This setup gives us a clear, organized collection of book records that we can easily manage and access later. We loop through each line in the list of lines, starting after the first line that holds the headers. By skipping the header row, every remaining line can be treated as a separate book record. For each of these records, we then extract the relevant data fields from that line for further processing. The code reads a line of text that represents a book record and splits it into separate fields using commas. Each field corresponds to a specific piece of information, such as the title, author, year, or shelf location. This process converts a raw text line into structured data. Once structured, the data can be accessed and manipulated more easily later in the script. We build a dictionary that links each column header from the CSV file to its matching value for a specific book. The headers list provides the field names, and the parts list provides the actual data for that book. By pairing each header with the correct value, we create a structured representation of a single book record. This completed dictionary can then be added to your overall collection of parsed book data. The code creates a dictionary for each book and appends it to a list of parsed books. This step is important because it gathers all the book data into a consistent, structured format. By adding each book dictionary to the list, the program builds a complete collection of book records from the raw CSV text, making them easier to access and work with later. The code prints a title before listing the parsed book records to clearly introduce what follows. This title signals that the upcoming information comes from the CSV style text. By doing this, the output gains context and is easier to understand. It also helps organize the display when multiple records are shown. We loop through each book dictionary in the parsed list so we can handle one book at a time. For every book, we create a single formatted description that combines its title, author, year, and shelf location. This description is built from the values stored in the current dictionary, making the information clearer and more organized. We then print this description to present a readable summary of each book's details taken from the CSV text. For each book, we build a short descriptive sentence using information stored in its dictionary. This sentence pulls out the title, author, publication year, and shelf location. By formatting these details in a clear, readable way, we turn the structured data from the raw CSV text into a human-friendly description. This makes it easier to understand and present the information for each book. This code prints a short description for each book record by building a single line of text that includes the title, author, year, and shelf location. It then sends this line to the console so you can see the information clearly. This demonstrates how structured details can be pulled out of raw text and displayed in a readable way. This script takes a block of CSV-style text with book records and converts it into structured data. It first splits the text into lines and uses the first line as headers for the title, author, year, and shelf. Each remaining line is then split into fields and matched with these headers to form a dictionary for each book. All these dictionaries are collected in a list, and the script finally prints each book's details in a clear, readable format. This shows how basic Python string operations can turn raw CSV text into organized data without using external libraries. Separated pairs. Separated pairs are a simple way to organize text data by writing a label, a colon, and then its value. This format is common in configuration files, where a setting name is followed by its option, and in logs, where a timestamp is followed by a message. You also see it in everyday lists, such as ingredients with names and quantities, or contact details with labels and their corresponding information. The colon acts as a clear divider, making it easy to split each entry into two parts for reading or further processing. When working with colon-separated pairs, treat each one as a record with a key on the left and a value on the right. The key names or describes the data, and the value holds the actual information. You typically read each line, split it at the colon, and trim any extra spaces. After that, you can standardize the key and store the pair in a data structure or use it directly in your program. This approach turns plain text into structured data that your code can process more easily. Colon-separated pairs can be combined with other simple parsing steps to handle more complex text formats. For example, in a settings file, you can split each line at the colon to separate the key from the value, then split the value by commas to get individual options. In the same way, details like a person's name, age, and city can be stored as separate colon pairs and then assembled into a structured record. By consistently using the colon as a boundary, you can turn informal text into organized data that is easier to process. Python code, colon-separated pairs. This script reads simple configuration-style text, where each setting is written as a key, a colon, and a value. For every line, it splits the text at the colon to separate the key from the value. It then trims any extra spaces around them and stores each cleaned key-value pair in a Python dictionary. The result is a convenient in-memory representation of the configuration data. This comment explains that the script uses only Python's built-in features, so you do not need to install anything extra. It emphasizes that the code is self-contained and does not depend on external libraries. As a result, it is easy to run and avoids additional setup steps or configuration hassles. We begin with a multi-line text that stores simple configuration settings, where each line has a key and a value separated by a colon. One line sets a username, another defines a maximum number of items, another chooses an imperial unit system, and another specifies a favorite length. This structure imitates a basic configuration file so that a program can read, parse, and use these settings automatically. We begin by printing a short message to signal that the original settings text block is about to be shown. Then we display the full multi-line configuration string itself. Seeing this raw input on screen lets learners verify its exact format and content, which is important for understanding and trusting the parsing steps that will follow. We begin by creating an empty dictionary called parsed settings, which will hold the key and value pairs extracted from the configuration text. Using a dictionary lets us efficiently link each key to its corresponding value. This structure makes it straightforward to access, update, and work with the parsed configuration data later in the script. We process the settings text one line at a time by splitting it on new lines, so each configuration entry can be handled separately. Any line that is completely empty is skipped, which prevents us from wasting effort on irrelevant content. This approach ensures that only meaningful configuration lines are passed on for further parsing and interpretation. This part of the code takes a line from the settings text and splits it into a key and a value, using the colon character as the separator. It tells the split operation to run only once so that any extra colons stay within the value and do not cause further splitting. This way, the key is cleanly separated from the value, even when the value itself contains colons. The result is a reliable way to isolate each settings name from its associated data. The code first cleans the key by trimming extra spaces and converting it to lowercase so that all keys are consistent. It also trims spaces from the value to keep it neat and ready to use. After cleaning, the key and value are stored together in a dictionary. This creates an organized structure that makes it easy and efficient to look up the data later. This step takes the cleaned key and value, removes any extra spaces, and stores them in the parsed settings dictionary. The key is converted to lowercase so all keys are consistent, while the value is left unchanged. This makes it easy to look up configuration settings later using their keys. The code prints a blank line to visually separate the original settings text from the parsed dictionary output. This creates a clear break between the two parts of the output. As a result, it is easier to see where the raw settings end and the processed data begins. Overall, this simple step improves the readability of the program's output. We go through each entry in the parsed settings dictionary and, for every key and its value, we print a message that shows them together. This lets us see exactly how each piece of the original text has been converted into a structured element. As a result, we get a clear, readable summary of the transformed settings data. This script reads a block of text that uses colons to separate keys and values, similar to a simple configuration file, and converts it into a structured dictionary. It first shows the original text, then creates an empty dictionary to hold the results. The script goes through each non-empty line, splits it at the first colon, trims extra spaces, and converts the key to lowercase for consistency. It stores these cleaned key-value pairs in the dictionary and finally prints each key with its value, demonstrating that the text has been successfully parsed and organized without using any external libraries. Checking parsed data. When you split a line of text into parts, you must still check that the resulting data is complete, correctly ordered, and makes sense before using it. Splitting only separates the pieces. It does not guarantee that values like a customer's email or purchase amount are present or valid. Verifying each piece helps prevent incorrect or misleading data from entering your program. This careful checking also makes your software more reliable and easier to debug when problems occur. When validating parsed data, make sure each field matches the format you expect. Treat non-numeric values in numeric fields like quantity or price as suspicious, and decide whether to ignore them or replace them with a default. For categorical fields, compare values against a defined list of allowed options and flag anything that does not match. Also check that dates follow a consistent pattern, currency codes are among the expected ones, and emails have a basic valid structure. Apply these checks systematically so you catch common errors without making the rules unnecessarily strict. When parsing data, you must check not only that the format is correct, but also that each record is complete and plausible. A registration entry might have all the expected fields, yet still be unusable if key values like the name, country, or ticket type are missing or invalid. In these cases, you might log a warning, store the bad record for later review, or mark it as incomplete so it is excluded from analysis. Treating parsing this way makes the process more robust and helps ensure that the data you rely on is trustworthy, especially when working with messy, real-world text files. Python code. Checking parsed data. This lesson focuses on checking parsed CSV-style data for basic correctness before using it. You will see how to confirm that each line has the expected number of fields and that simple value formats look valid. The goal is to show safe, beginner-friendly checks so you can trust that each parsed text line is reasonable. By validating field counts and basic formats, you reduce errors and make your data processing more reliable. This line explains that the script only uses Python's built-in modules, so you do not need to install anything extra. Because there are no external dependencies, the code is easier to run and manage. This makes the script more accessible and more likely to work smoothly in different environments. We begin with a list of strings, where each string represents one line of CSV-style purchase data containing a name, an email address, and a purchase amount separated by commas. These lines act as sample purchase records that the code will process. Using this setup, we can test how well the code parses each record and validates the fields. In particular, it lets us check for problems such as invalid email formats or purchase amounts that are not numeric. We set the expected number of fields in each parsed record line to 3. This defines how many pieces of information each line must contain. Having a fixed number of fields keeps the data consistent and makes it easier to check that each line matches the required structure later in the script. This part of the code defines a small helper function that checks whether a piece of text looks like an email address. It takes a string as input and returns true if the string contains both an @ sign and a period. This is a very simple way to confirm that the email field has a basic email-like structure. Using this check helps with initial data validation before the information is processed further. The script begins by printing a header line that tells the user it is about to check the parsed purchase records for problems. This message signals the start of the validation step. It prepares the user to see a list of any basic issues or suspicious values found in the data. In this way, the header clearly frames the purpose of the upcoming output. We process each entry in the list of lines by taking one line at a time as a raw text string. For each line, we split the text at every comma, which breaks it into separate pieces. Each piece corresponds to a different field from the original line. This separation is essential because it allows us to validate and handle each field individually in later steps. The code verifies that each line has the correct number of fields by comparing how many parts it contains after splitting with the expected count. If the numbers do not match, it reports that this line has the wrong number of fields. It then skips any further work on that line and immediately moves on to the next one in the loop. The code takes the list of values from a CSV line and assigns each one to a specific variable, such as name, email, and amount text. By unpacking the list into clearly labeled variables, the code becomes easier to read and understand. This approach also makes it simpler to use each piece of data correctly in later validation steps. The code first cleans the customer name by removing any spaces at the beginning or end. It then checks whether the cleaned name is empty. If it is empty, the code reports that this line is missing a customer name. After that, it uses a command to skip any further processing for this line and immediately moves on to the next line in the dataset. The code first removes any extra spaces from the email field, then uses a helper function to check whether the email has a valid structure, such as containing an @ sign and a period. If the email fails this basic validation, the code marks the current line as problematic, prints a warning about the suspicious email format, and skips any further processing for that line by moving on to the next one in the loop. The code first trims extra spaces from the amount text to clean it up, then tries to convert this cleaned text into a floating point number so it can be used in calculations. If the conversion fails, meaning the text is not a valid number, it prints a message identifying the problematic line and skips to the next record. This way, only valid numerical data is processed further, and invalid entries are safely ignored. The code validates each purchase amount by checking that it is positive and within a plausible upper limit. It first confirms the amount is greater than 0, so it is not 0 or negative. Then it ensures the amount does not exceed 10,000, which is treated as the maximum reasonable value. If either condition is not met, the code reports that the line has an implausible purchase amount and stops processing that line further. When all checks for a line of data pass, the program prints a confirmation message. It reports that the record is valid and includes the customer's name, the amount they spent formatted as dollars with 2 decimal places, and their email address. This message serves as a concise summary of the verified information. It confirms that the record satisfies all the required validation rules. This script checks a list of CSV-style purchase records to make sure each one is valid before further use. For every line, it splits the text into 3 fields and verifies that there is a name, a properly formed email containing an @ sign and a period, and a purchase amount that can be converted to a positive floating point number within a reasonable range. If any of these checks fail, it reports what is wrong with that record. If all checks pass, it confirms the record as valid and reports the name, amount, and email, helping maintain data integrity in the dataset. In this lecture, you learned to use split to break strings into lists based on separators, process each part of a split string using loops and simple conditions, and apply basic parsing to simple text formats like comma-separated values. In the next module, Module 7, we will go over files and data.
Thank you for your attention. See you all in the next lecture.